Example 2. A sled is going down an icy frictionless hill that makes an angle alpha with the horizontal.
The sled has an initial downhill speed v1 at the top of the hill. It travels a distance L down the hill before immediately going on to an uphill ramp that makes an angle beta above the horizontal. The coefficient of kinetic friction between the sled and the ramp is mu k. What is the distance that the sled moves up the ramp before coming to rest?
All right. So let's draw a picture. So it's going down an icy frictionless hill that makes an angle alpha with the horizontal. So that looks like that. And let me draw the sled. I'm going to draw it as a box. It can be anything. And I'll just draw it as a box. And the sled has an initial downhill speed v1 and it travels a distance L down that hill. So from like this point down to here, that is L.
Just
Oh,
take the L.
yeah, take the L. And then before immediately going onto an uphill ramp that makes an angle beta with the horizontal. So let's say that looks like this. This is beta. And I'll just label when the box reaches this point right here. All right, so it goes on that ramp, and that ramp has friction with the sled. It has coefficient of kinetic friction mu k. So what is the distance that the sled moves up the ramp before coming to rest? So let's say it goes all the way up there, and then it's at rest. Let's call the distance that it goes up d. And let me label some stuff. When the sled is at the top of the hill, I'm gonna call that 1. Alright, so this height right here is y1. And then when it switches over to the ramp, I'm gonna call that 2. And when it's at rest on the ramp, I'm gonna call that 3. So this is y3 right here. So we're trying to find d, so we have to look at what's happening between 2 and 3. So let's write our energy equation for 2 to 3. Okay, so we have K2 plus UG2 plus US2 plus the work done by the non-conservative forces equals K3 plus UG3 plus US3. So K2 is 1 half mv2 squared. That means the sled has a speed v2 at the bottom of the ramp that we don't know. So we don't know m and we don't know v2. So that's two unknowns there. UG2, remember, gravitational potential energy at position 2. Gravitational potential energy is mgy. And what's y at position 2 if I define y equals 0 as this line right here? So it's basically at y equals 0. So at position 2, the gravitational potential energy is 0. US2, are there any spring forces in this problem?
Not that I can see, although that would make it even more interesting.
Yes, there are no spring forces. So US2 and US3 are both 0. Work done by the non-conservative forces.
Friction.
Yeah, the only non-conservative force that's acting on the sled between 2 and 3 is friction, right? Let's actually label the forces. We got mg, we got the normal force, and we have friction. Normal force is not doing any work because it's perpendicular to the displacement. And gravitational force is a conservative force, so the only non-conservative force is friction, specifically kinetic friction. So this is the work done by kinetic friction. K3, that's 1 half mv3 squared. What's v3?
0.
Yeah, it says what's the distance that the sled moves up the ramp before coming to rest. So at this position 3 right here, the sled is at rest. So v3 equals 0. So that means k3 is 0. All right, and lastly, ug3. I called this height right here y3. So the gravitational potential energy at position 3 is just mg y3. Okay, so that's what the energy equation reduces to. We're trying to find d, but there is no d in this equation. So we have to rewrite some of these variables. Let's start with the work done by friction. So remember the work done by friction, it's Fs cosine phi. So F, the force is F sub k. S is d in this case. That's the magnitude of the displacement. So d, and then cosine phi. All right, and then we have mgy3. So what's y3? It doesn't give us y3 in the problem, but
We know beta.
yeah,
We got that D, so we can just do a bit of trig, you know?
yeah, sine of beta is opposite over hypotenuse, so y3 over d. So I can write y3 in terms of d. I can say that y3 equals d times sine of beta. All right, so this becomes mg d sine beta. And remember, we're trying to find d. We have a couple of unknowns here. We don't know m, we don't know v2, we don't know the force of kinetic friction. We're trying to find d. We can find phi pretty easily. Let's start with the force of kinetic friction. Is there a formula we have for F sub k?
Yes, that would be mu k times the normal force.
Yeah. So Fk is mu k times n. And then we have times d. And what's phi in this case? The displacement is in this direction.
It's 180 degrees.
Yeah, so the angle between the frictional force and the displacement is 180 degrees. Okay, so we have the coefficient of kinetic friction that's given in the problem, but we don't have the normal force. So what do we have to do to find n?
And we can just do F equals ma.
Yeah, so we have to use Newton's second law. So I'm going to define my coordinate system. I'm going to make one axis parallel to the ramp. So that's the parallel axis, and then one axis perpendicular to the ramp. So that's the perpendicular axis. Okay, so to find the normal force, we have to look at the sum of the forces in the perpendicular direction because the normal force is in the perpendicular direction after all. So the sum of the forces in the perpendicular direction equals ma in the perpendicular direction. So in which direction is the acceleration pointing? The sled is slowing down, so the acceleration is down the ramp in the negative parallel direction. So let me label that. So A is not in the perpendicular direction at all. So A perpendicular is 0. And the sum of the forces in the perpendicular direction is just going to be N minus mg in the perpendicular direction. So let me break that up into its components. All right, so the sum of the forces in the perpendicular direction is just N minus mg perpendicular. And like I said, A perpendicular is 0. MG perpendicular is what?
Mg cosine beta.
Yes, because cos keeps it close.
Who told you that?
I learned it from a very wise person. So if you want to just know the angles, this is beta right here. And since MG perpendicular is adjacent to that angle, MG perpendicular is MG cosine beta. All right, so if I add mg perpendicular to both sides, you'll get n equals mg cosine beta. Right, you could have looked at it and known that, but like I just want to verify it. Okay, so I can replace n with mg cosine beta now.
And let's replace cosine 180 with -1.
Yeah, and cosine of 180 degrees is -1, so I'm going to subtract this, and n is mg cosine beta, and I'll put the d in between the g and the cosine beta. And this equals mgd sine beta. So what do you notice is going to happen now?
M, it's gone.
Yes, we can divide both sides by m, and all the m's will cancel. So that's great because that was one of the unknowns. The problem doesn't tell us anything about m. So we don't have to worry about it anymore. So we have beta. We're trying to find D. We know G, that's just 9.81. We know beta, trying to find D. We know G. The problem gives us mu K. The only thing that we don't know other than D is V2. We don't know the speed of the sled at position 2 right here. To figure that out, we have to use the energy equation from 1 to 2.
Or kinematics, but we can do that as well.
Yeah, we'll just do energy for everything. I'm just gonna rewrite this with ones and twos instead of twos and threes. Okay, so let's look at the forces acting on the sled at position 1. So we have gravitational force, we got mg, we got the normal force. Is there anything else?
Well, no friction.
Icy frictionless hill. So those are the only forces, just N and mg. So there are no non-conservative forces from 1 to 2. So WNC is 0. The normal force does no work because it's perpendicular to the displacement. Okay. We also have no springs, so US1 and US2, that's 0. K1 is 1 half mv1 squared because the sled has a speed v1 initially. UG1 is mg y1 because that's the height at position 1. K2 is 1 half mv2 squared. And UG2, we said earlier, is 0 because y2 is basically 0 at that point. So that cancels out. So we have V1 that's given in the problem right here. Y1, we don't know that, but we can write it in terms of alpha and L, which we do know. We know sine of alpha, it's opposite, which is y1 over hypotenuse, which is L. So if you multiply both sides by L, you get y1 is L sine alpha. And I can also divide both sides by m, and these three m's will cancel, which is good because we don't know m. So you get 1 half v1 squared plus gl sine alpha, and that equals 1 half v2 squared. We don't even need to find v2. We can just leave it as 1 half v2 squared because we have 1 half v2 squared right there. So I can just substitute all of this stuff. Just substitute all of that. We're trying to find D. So these are the two terms that have D in it. So I'm going to move them all to the same side. So I'm going to add mu k gd cosine beta to both sides.
It's basically a math problem, not a physics problem now.
Yeah. Okay, so we're trying to find D. So what I'll do is I'll factor out the D on the right-hand side, and I'll divide both sides of the equation by G since G is popping up a lot. So you'll get V1 squared. Instead of times 1 half, I'm going to write divided by 2, and I also divided by G. I divide by G, so this will cancel, so it just becomes plus L sine alpha. Again, I divided by G and I factored out the D. So the right-hand side becomes D times sine of beta plus mu k cosine beta. All right, so the last step to find D is divide both sides by sine beta plus mu k cosine beta.
Looks prettier in variable form.
Yeah. So let me just quickly double check. The problem gives us V1, so that's good. We know G. The problem gives us L. The problem gives us alpha as well. The problem gives us beta and mu k. So I wrote D in terms of everything that was given in the problem and the constant G. So we're good. All right. So that's the power of using these energy equations. And that's pretty much all I got. Make sure to like and subscribe, and I'll see you guys soon.
Bye.